Welcome, everybody. How did this last week go for y'all? How'd y'all feel about it? Let me know. And I hope y'all are staying cool because where I'm at, I don't know where y'all at, but where I'm at, man, it's hot. But I'm gonna give it a couple more minutes for more people to join in too before we get started. Um, for this one, we're gonna go over the linked list implementation. That's the project from the second week, and then next week I'll do the next project, and then so on and so forth. Give it about 30 more seconds. Can y'all hear me okay? Put a one in the chat if y'all can hear me okay. Just so I know the audio is good. Okay, bet that. All right, so I'm about to share my screen. So like I said, I'm going over the, let me know, can you see the screen? But this is the one I'm going over, the linked list implementation. Okay, so to first go, so before we get into the implementation, I want to explain a little bit about what a linked list is in the first place. So the project before we did an array, right? And with an array, all the objects, everything that's saved, it's saved sequentially. So it's all in order, right? So in the disk on memory, it's saved on the 0 index, first index, second index, third index, so forth and so on. So they're right next to each other. And you can kind of think about it like a line at the store. Each customer is back to back to back to back to back. That's how it's stored in memory when it comes to an array. Now, with the linked list, instead of everything being stored contiguously, it's stored. The memory can be stored anywhere, right? Or the data can be stored anywhere in memory. And how a linked list works is you have the data itself, and then it has a pointer to the next piece of data. It has a pointer to the address of the next piece of data, right? So you can kind of think about it like imagine you're doing a treasure hunt, right? And you got to find a clue, then you get the next clue, get the next clue, get the next clue. With an array in that treasure hunt, all the clues would be on one piece of paper or in one tablet or packet, right? But with the linked list, the clues, so you'll get the first clue, and then the first clue will tell you the address of the second clue. Then you got to go to the address, and now you're at the second clue. That second clue would have the clue and the address to the third clue. The third clue would have the clue and the address to the fourth clue, right? So that's what a linked list is. You have the data, and then the memory address to the next piece of data. Does that make sense? So the first clue, that's what we call the head of the data because it's what starts off the data, right? It's like basically the 0 index. That's called the head, right? The last clue, you can call that a tail. Sometimes you can, when you implement your linked list, you can implement it with a tail. So you can just start from the tail. It'll help if you wanted to, it will help if you needed to keep track of the tail. But in this implementation, we're not going to do that. But doing it would you still could, but we're not doing it for this exact implementation. Yeah, so I'm hoping everything I said so far is making sense, right? So each of this combination of the data and the pointer to the next, that chunk right there is called a node. So again, with the treasure hunt, each clue will be called a node, and then the node includes the clue and the address to the next node or the next clue. So we just did the array. Now we're on linked list. So you might ask yourself, why not just use an array, right? And the reason you wouldn't just want to use an array is because when it comes to, because sometimes you have to shift the order of things, right? So with an array, if you have A, B, C, D, but you want to put E right between A and B, then D has to slide over, C has to slide over, B has to slide over, and then you have that spot for E. So you see that shift that has to go on? Or if you want to remove B so it can be A, C, D, if you want to remove B, then you remove B and then C has to slide over and D has to slide over. So that's what has to happen in the array. So it can work, but it's not efficient. A linked list allows that to be more efficient because now you can just get, so with the linked list, it would be A points to B, points to C, points to D. And to insert, all you have to do is have A point to B. I mean, A point to E, and then E points to B. So it's a lot faster. It's something that can get done in all of one time. So it makes that a lot more fast. So that's why that's when you would use a linked list, right? So if you need constant inserting and deleting, it's better to use a linked list. And if you're doing constant lookups, that's when you want to use an array, right? Because remember, the lookup time for an array is O of 1, right? So that's when that's the difference between a linked list and an array, right? Actually, let me show you. So if I was to, so with an array, it'll be A, B, A, B, C, D, right? And then I'd want to turn it into, let's say I want to add E before A, B, I mean, between A and B. I want to do this, right? But in order to get to here, I would have to go through this process of having A, then I'll delete B, or not delete B, but I'll have to, matter of fact, let me do this. This might make it better. I'd have to do this. So first, I'd have to shift D over. First, I got to create that space and shift D over. And then A, B, C, and then D. And then that'll go to space C D, and then that'll go to A space B C D. And then I can add E. So if I want to add E, I have to go through this whole process right here, right? If I want to add E, I have to go through this whole process right here with an array, specifically. Add E array. Add E linked list. So with a linked list, I would have A pointing to, first I'll start off with that, to B pointing to C pointing to D, right? But to add E, all I have to do is to move this pointer to point, have that pointer point straight to E. So instead of pointing to B right now, I'll just make it point to E, and then I have E point to B, right? You see how I don't really have to shift anything? Because remember, with an array, they're all right next to each other in memory, so things have to be shifted. With a linked list, they can be anywhere, and they are anywhere in memory, right? So it's not necessarily in order. So with the pointer, you can just have everything set, right? Boom, 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 boom. So we talked about the node. So as we see, we have this node class right here. Let me actually take this out so it doesn't get confusing. Oh, shoot. Let me put it up here. Okay, boom. So with the linked list, like I said, you need the node. And in the treasure hunt example, the node is going to be the card that the clue is on, and the same card that has the address to the next clue. So the card is what a node is. So we'd have to classify a node, which just has data, which is the clue, and then it has next, which is just the pointer to the address, right? And we have next at none, because every time you're adding a clue, there is no next clue yet. You haven't put the next clue yet. So if there's no next clue yet, then it's just null, right? Everything making sense so far? And then this is the class for the linked list. But is everything making sense so far? Let me see. Okay. Okay. So with the linked list, we have head. Oh, my bad. I just realized we are doing tail. Okay, boom. So with the linked list, we have self.head and we have self.tail. And then we also keep track of the size. And the functions that we're going to be doing are add, where we're adding an element to the end of the list. And we also have a note here to update the tail and the size. Boom. We're doing insert, which is insert an element at the specified index. So remember the difference between add and insert. Add is just adding straight to the end, and insert is inserting at a specific spot, right? Then get is getting the first element, or we're getting an element at a specific index. Remove, we're just removing the element at the specific index. Size, we're returning the current number of elements in the linked list, so just returning the size of the linked list. And then is empty, that's just us checking to see if the linked list is empty, right? Boom. And honestly, this is already the way is empty is already it already works. So and then the same thing with size, honestly. Yeah. Size and is empty. They already work. So we won't really have to worry about them. The only thing is we do have to make sure that our code is accurately keeping track of the size, because that's the important parts of it, right? So when it comes to, let's walk over adding to a linked list. I did just give that walkthrough. Um, but I actually want to show it right here in the function. So what are the things that we're doing? What are the things that we know is the input with the, oh shoot. The input that we're getting when adding to a linked list is we're just getting the element, right? And then for the output, what are we getting? We're not really getting anything for the output. Why? Because you're not returning anything. You're just growing the linked list. So no, we're not actually expecting to get anything in return. We just have to make sure when we're adding, we have to adding and inserting those two, we have to make sure that they are properly added, right? You don't want to assume you added and then you go check for that item and that item is not there, right? So that's the thing about adding and inserting, right? So boom. And then what are some things? Let's see. So now we want to ask ourselves some clarifying questions, right? Let me do this, make it easier to read. Okay, boom. So when it comes to a linked list, what are some clarifying things, some clarifying questions that we want to ask when we're trying to add, right? So if we know, okay, we have to add this element, right? Are we adding to a list that's empty? So we can ask ourselves, is it an empty list? We can ask, do we have one node or many nodes? Right? Because as we see here, we're keeping track of the tail and we're keeping track of the head. And that's actually perfect now. Yeah, the fact that we're keeping track of the tail, let me add that. Let me add the fact that we're keeping track of the tail is actually perfect. We can use that, keeping track of tail. Yeah, that's actually perfect to use when it comes to adding, right? And the reason I say it's perfect to use is because if we weren't keeping track of the tail, then every time we wanted to add, we would have to traverse the whole linked list. And then once we got to the end where node that next is equal to none, then we'll be able to add, right? Because we wouldn't know where the last node is in memory. We would have to start from the beginning, start from the head, and then make our way over. But if we're keeping track of the tail, then we know where the start is and we know where the end is, right? The start is the head, the end is the tail. So now that we know that, if we want to add, we could just start at the tail and then do node that next of the tail point to the thing that the element that we're about to add. Once we add it, then we change that, we make that new node the actual the actual the actual tail, right? So that makes it easy. So knowing that we're actually keeping track of tail, that's important. So when we're adding, so we have our element, but we have to take that element and then actually store it in the node, right? So the first thing that but in order to store it in the node, what do we need? We need to create that node, right? So in order to store it to the node, we have to first create a node. Because if there's no index card to write the clues, or there's no card to write the clues, then you can't write the clues, right? So first you have to create the index card. After that's created, what do we ask here? Is the list empty, right? We have to ask ourselves, is the list empty? So we'll say, okay, if the list is empty, then we know, okay, we have to set the head to our current node, right? We have to set the head to the node that we've created, right? Because it's empty. So this node is going to be the head. And then because it's empty, not only is this node the head, because it's the first, but it's also the tail. Why? Because it's the end of the list. It's the first of the list and the end of the list, because it's only one thing at the end. I mean, in the list. So we're going to have tail and head both equal node, right? So boom. Now, if it's not empty, what do we do? Like I said, if it's not empty and we're keeping track of tail, all we have to do is take tail that next and set that equal to node. We'll have tail that next equal to node. And then we're gonna set tail to be node, the created node. Boom, right? And then once we've done that, we got to remember to increase the size, because we're keeping track of the size. We want to make sure that the size is accurate, right? So when it comes to adding, it's literally that simple, right? First, you create the node. You check if the node is empty. If it's empty, then you set head and tail to be that node. If it's not empty, then you go to the tail and set tail that next to be that node, so it comes next in the list. And then you set tail to be that node. So next time we look for the end of the list, we're updating tail, so because we just added to the end of the list, right? So boom. Now we've figured out our inputs, which is the element. We figured out what we're supposed to return. And in this case, we're not returning anything. We have our clarifying questions. Is it an empty list? Do we have one node in the list? Do we have many nodes in the list? Right? And then boom, now we can walk through exactly what it is. And this is without actual code, right? And actually, if list is empty, that's actually a little easier to read. So now we can literally just go line by line and actually create that code, right? So the first thing we do is this right here, create a node, right? So we're gonna have a new node and we're gonna set that. Remember, I think the class was capital N. Yep. It's a capital N for the node class. So node and is gonna be element. And actually, let me do this. I'm gonna go one by one with the pseudocode, right? So we can actually see the importance of pseudocode. Because remember, pseudocode is where Pseudocode is where we get our logic, right? That's where we make sure our logic works. That's what the pseudocode is for. It makes sure that our logic works step by step. Then when we go to the actual code, and the importance of that is because when you get to the actual code, you don't want to be worried about logic at that point. You just want, if you're going to have any problems, you just want it to be syntax problems, right? If you have any logic problems, you return to your pseudocode and check the logic there. With the actual code, let that only be syntax when you're actually coding. Because at least you know, okay, boom, my logic works. It's going to be easy to debug if I know my logic works. And it's easier to debug with pseudocode. It's easier to debug logic with pseudocode because it's just English. It's not actual code. It's not syntax, right? So, but when you already know what the logic is line by line, then you can figure out what the syntax is. It doesn't even matter what language you're using, whether that be Python, Java, Ruby, C++, it doesn't matter because you know the logic you're going for, right? So that's the thing. And a lot of the times in these interviews, if your logic makes sense, then they might not even care if you were able to finish the code out or not because they understand your logic, right? So that's the importance of it. You want to separate syntax and logic. Make it as easy on yourself as possible. That's why it's so important. Boom. So that was that. The next thing. So we said, okay, if list is empty, and the way we check this is if self.head is none, right? If we don't have a head. Or I guess you can also check it by the size, but we haven't. Well, yeah, either way, you can check if self.head is none, or you can check by the size. Either way, it gets you to the same thing, right? So here we're going to have self. We'll set self.head to equal new node. And in here, we'll have self.tail. And that'll be equal to new node, right? And then let's go to the else. And again, you see how I'm literally just going line by line, just line by line with the pseudocode. That's literally it. So here we know, okay, tail that next. Oh, shoot. Tail that next equal to new node. Oh, shoot, I forgot self on this one. That would have been a bug right there. Boom, boom, boom. And then the next thing we do, increase size, right? Oh, shoot, it's a bug in here. And that'll just be self. And then increase it by 1. Boom. And you see how we literally just went through for this. We just went through again. I keep saying it because this blueprint, having a blueprint is super important. Really understanding what it is that the input is, what is your output, and then understanding your goal, right? Those is very important because those are the foundations of answering the problem. Because if you can't even answer the problem if you don't understand the problem, right? Now that you have your input, output, and your goal, you ask yourself some clarifying questions and try to figure out some edge cases. Like, what are some things that'll break the code, right? Or what are some things that you'll need to know? Okay, boom, is my list empty? Does it only have one thing? Does it have many things, right? Because if it's empty, then I have to treat it one way. If it has one node, I have to treat it one way. If it has many nodes, I have to treat it one way, right? And then from there, you break down, okay, what do I have to do if it's empty? What do I have to do if it's only one node? What do I have to do if it's many nodes, right? From there, as you start understanding the problem, now you build your pseudocode where the sole focus on pseudocode is just understanding your logic or making sure that your logic makes sense. And then once that makes sense, then you go into coding out your logic. And this is where it just becomes syntax oriented. Boom. So now we'll go to insert. So what are the things with insert that we have to figure out, right? So we know that with insert, we got a couple of things. With our input, we're getting an index. Oh, shoot, wrong one. There we go. So with our input, we're getting an index and we're getting an element. Okay, boom. So now I know those are the two things that I'll be using. And then output, again, this doesn't require, it's not returns nothing. Nothing to return. Okay, boom. So now some clarifying questions or edge cases, right? So when it comes to inserting, what are some things that we're going to need to know, right? We're going to have to check. Is this empty? Right? The same way we had to ask while we were adding, we had to check. Is this empty? Right? And then the reason, and then what's next after we check if it's empty? We check, okay, remember we're getting an index. Oh, shoot. So we're getting an index. Knowing what an index is the index is going to be the position on the list, right? So what happens if we have a list of 7 items, right? And somebody says, okay, the index that they give us is -1 or -2 or -3, right? We can't do anything less than 0 because that's not valid, right? It's either 1, 2, 3, 4, 5, 6, or 7, right? There is no negative spot, right? So we know, okay, is given index negative. So we know we have to check that. Boom. Now, on the flip side of that, we also have to check, is the given index is the given index greater than the current size of our list? Because if the list is of a size 7 and the given index is a 10, that won't be able to work, right? So boom. So we have to check, is this empty? Is the given index negative? Is it positive? Right? And then from there we can start working. So now we know, okay, pseudocode. So first, we're gonna do a validation check on the index to make sure that it's in range, right? And if it's not in range, we're just gonna return an out of bounds error. Boom, we got that. And now we want to know, are we oh, that's another great question. Inserting at front or end, right? If we're inserting in the front half, then we'd want to start traversing from the head. If we're inserting on the back half, we want to start traversing from the tail, right? Because if you have a list of 10 nodes and you want to insert at index 7, it wouldn't make sense to start from the 0 or from 1, because now you have to traverse all of that, when it would be faster to start from 10, right? So that's something that we'd have to check, right? So after we validate, we'll check. Okay, so if let's say inserting, if inserting at the front, so we're gonna check that, and then we'll check if at the end, and then walk to previous node. And then we're gonna have the new node the new node that next set to the previous that next, right? And then we're gonna increase size. Boom. Now we're ready to build our linked list insert function, right? And again, we're just gonna walk through this as the pseudocode shows us. We're gonna start off with that index out of bounds check. So if it's less than 0, or if index is greater than the size, then we'll just raise that index out of bounds error. And we'll just say index out of bounds. Boom. So we've done our check. Then we're going to create that new node. With that element. Now, this is for if we're inserting at the front, right? So if index is equal to 0, then new node that next is equal to self that head. And then self that head is now the new node. Boom. And then if size is equal to 0, then tail is also equal to new node, right? Remember, we have to keep track of tail, head, and size at all times. Now, if index is going to be at the end, so we're going to check that by seeing if the index is equal to size. And in that case, tail.next is equal to new node, right? And then self.tail becomes new node, right? So first we have to do tail.next to make sure the information is there. And then we actually pass it on. Make sure syntax is right. It's looking right. Okay, boom. Now if we're inserting in the middle, then we'll have current with a self.head. Index on this one. I have current at next. And then new node dot next is going to be equal to current dot next. Boom. Now current dot next equal to new node. Boom. And then when we're done with that, like we said in our pseudocode, we're going to update self that size. Boom. So now we have, I hope, so far is everything making sense to everybody? Okay, bet that. Now for get. Actually, get is actually pretty simple. So let me do remove first, right? Because get size and is empty, or well, size and is empty. We don't even have to touch, honestly. Yeah, we don't have to touch. It already is what it is. So I'll do remove first. And then I'll end off with get. So with remove, we get the index. And what do we know about when we get an index? We have to check to make sure that index is available to remove, right? So that index out of bounds error. X is greater than, right? And then that's when we'll raise the index error. Okay, boom. Then we're going to remove that first node. Boom, we removed that first node. Oh, shoot. And then we're going to check if the linked list is empty. Because remember, we have to update the tail. Right? Boom. So that's if we're removing the first node. If we're removing a different node, then okay, then we're going to have to this of that head. then previous equal to previous then next. Okay. Boom. And then we're going to have previous that next set to remove that next. And then if removed is the tail, remember we got to update. Oh, that is a semicolon. If removed is equal to tail, then we'll set the tail to previous. All right. And then once we've done that, like always, we have to update size. And in this case, since we're removing, we knock down size by 1. And then we're going to return remove that data. Boom. Now with get, all we're doing with get, like I said, get is pretty self-explanatory. All we're doing with get is we're traversing the linked list until we've gotten to the index, right? The only thing that we have to remember when it comes to this again is the index out of bounds check. That's it. And then after that, all we're doing, we'll have a current pointer that starts at the head. We have a current pointer that starts at the head. And then we're just going to keep looping until we get to whichever one has the data, right? Or not even the data. We're going to keep looping until we get to the index. It's the same thing as with the array. You start at the beginning and you loop. Well, not necessarily, because the array is all one lookup. So you're not actually doing that, but you're just traversing the list. So going from with the treasure hunt example, you're starting at clue 1, you go to clue 2, go to clue 3, go to clue 4, until you find clue number 7, right? Because let's say 7 was the given index, right? So we're gonna keep making whatever we currently at equal to the next one until into the index. And then once we've gotten there, all we do is return the data. That is literally it. And just like that, we went over every single thing. Like you guys seen, especially with add and insert, you see how the process makes solving these problems intuitive, right? I did go a little quicker just because I've been harping on it so much, but so I know y'all are starting to understand it, but I still do want it to be shown and seen that it is important to go through this blueprint. If you just start off trying to go straight to code, that's when you start your brain doesn't even know what to code, right? So if you just jump right into code, it's gonna get you stuck. You're gonna mess up and you're gonna feel like So to just cut off the stress, step by step, just walk it through. And as you're walking through, you're just gonna naturally get to the answer, right? As you walk through, you're just gonna find the answer. Sometimes there's problems that I don't know how to solve, but as I go through, I just end up landing to the answer because it ends up just making sense. The answer starts making sense as you break it down because you start seeing the edge cases, the inefficiencies, and all of that. So when it just starts to become obvious and you have it all written down and drawn out and it's obvious, then it's like, oh, duh, right? But if I go straight into code, that's when my mind starts going, it starts going blank because now I'm trying to think of the code line by line and I'm trying to make it make sense in my head. But it's like, nah, just follow the process. So let's run it. Boom, all test cases passed, submit it, and then even the 5 secret test cases passed. So as you see, there are other ways that you can solve each of these. Well, I guess except for like get. Well, it's other ways. Yes, it's other ways you can solve these. This is just the way I went about solving it. But like I said with add, because I know with add, let me see. With add, what was it that I spoke about with add? It was something. It was something. All right. With add, I checked if self that head is none. You can also check based on the size. You can get the size. If size is 0, then you know it's empty. So, like I said, it's little small tweaks that you can make to that just fits your mind and whatever makes sense to you. So, yeah. Thank everybody for joining me here on stream. If you have any questions, you can always hit me up on Discord. So I have the Discord link pinned into the chat. And also if you have any questions right now, you can ask me the questions. But Discord is where you can find us at any time. So 24/7, you'll find us on Discord. If you ask a question and we're not able to get to you right away, just know not too long from now, just give it a couple hours and then we'll end up getting back to you. But you hit us up on Discord, it's pinned in the chat. And like I said, thank you guys for joining me. I will see y'all next week.